Hello, everyone. This series of lectures is on the C programming, the essentials that you need to be able to write simple and effective C programs. There is a lot in terms of pointers, structures, and so forth that I will not cover in these slides. The intent is not to have a comprehensive introduction to C language, but rather a minimalist approach so that you can be able to write programs and be comfortable with the C language to the point that you can extend your C skills on your own using other resources. All right, so very quickly, a little bit of history of C language. C language was developed by Dennis Ritchie and Robert Kernighan. Since then, it has become standardized. The standard C is standardized used by American National Standards Institute, ANSI. Typically, when you want to use a compiler to translate your C code to a machine code, you want to make sure that you do use an ANSI compiler so that it generates and understands standard C language. Just getting ahead of ourselves a little bit so that you're aware that C language is a very, very minimalist language. It has very small number of keywords. So the C 77 standard, which is the 1977 version of the standard, has, well, actually C89, has 32 reserved keywords that you see in here. That's it. All of the keywords in the C language are listed in here. And then C99 added 5 additional keywords, which we won't be using in these slides. So the number of keywords to memorize and use in C language are very small. In fact, you won't be using probably half of them. So you're looking at about 16 or so keywords that you will be using most of the time. An important concept to remember in any programming language is that the programming language supports you, the programmer, by providing you a lot of pre-written code. Okay, the idea here is that if I am writing a piece of, let's say, scientific program, and I need some mathematical functions, it's not really expected of me to start and write down a program that computes the square root of a number, or the exponential of a number, or tangent, or sine, or any other math functions that you can imagine. So the concept is as follows. The developers of the tools will write a bunch of code. They'll compile them, they test them, they debug them. Once the code is perfectly acceptable, then they pre-compile them into modules called libraries, okay? And what that means is that when you want to write your code, you simply call a function that exists within these libraries, and at the execution time, you will see that that function will actually get executed. So effectively, you're using the code that is written by somebody else, and you include it as a library in your code. Any programming language has libraries. C has a number of ANSI libraries for math functions, for standard I/O that people use a lot, string operations, and so forth. And other languages have libraries that, in many cases, are far, far more extensive than C. C actually, again, has a very minimalist approach to having libraries. Programming languages such as C++ and particularly Java have much, much bigger libraries, which means that you can do all sorts of things, very, very sophisticated things, simply by calling the appropriate library functions in your code. Again, knowing the syntax, the keywords, and the format of a language is one aspect. Knowing which library functions are available is a much, much bigger thing. Okay, so as you will see in your other courses, if you haven't, for example, the syntax of Java language is not that different from C language. but then there's so many libraries in the Java language that you can use that really the expertise comes from knowing which library functions are available and where to use them. Okay, so very quick overview of the development cycle for any programming language, and I'm going to just simplify it basically to the context of what we're working on. So you write your C code in an editor. So you type in text into an editor and save it as a .c file. That's text file that is only good for you and me. Computers will have absolutely no appreciation for it. So you will feed your C code to what is called a C compiler. The compiler is a program that translates your high-level C language statements into the assembly language instructions for a particular processor. So if you're running it on the on a PC, it will translate it into the assembly language for the Intel processors. If you're running your compiler on a Raspberry Pi, it would translate it to the assembly language instructions for the ARM processor, and so on and so forth. Then the assembly language instructions that were generated out of the compiler are fed into what is called an assembler. An assembler does a one-to-one translation between each of the assembly language instructions and the binary equivalent, essentially the machine code, right? So it generates an object file, which essentially is a sequence of binary values. Each binary value would be the binary code for one particular assembly instruction that constitutes your program. Now, if you had libraries, or library calls rather, in your program, which most of the time we do. For example, we use printf a lot in our programs, which is a standard I/O, standard input-output library function. So those calls from the libraries will be recognized at this point, and a tool called linker will link code generated by you and the code that has been generated in the libraries, and generates the final executable file. Okay, so the executable file is the file that actually contains the program that you can run. Now, these programs manifest themselves differently. In the Windows environment, it would be a file with an extension exe, and we will work on it in the C programming exercises in the beginning. And in other environments, it really depends on the platform. If it's a Unix, Linux-based environment, it's a binary file, typically with no extensions, with a dot at the end of it, and it could take other forms in other embedded devices. Okay, so this is a very quick walkthrough of the tools that are available to you. And of course, if you're running your program in the, on a PC or on a laptop, it is essentially your debug environment, as we initially will, but also recognize that you may have your code running on an embedded platform that has no Windows debugging capabilities, which means that then this option does not exist. So enough said on that. So let's start digging in and understanding the different components of a file that contains a C program. So first we need to understand what the C preprocessor is. Okay, it's a very important concept that you need to understand ahead of time and not worry about it ever again. The C processor is nothing more than a text substitution tool. It doesn't do any translations of any language to any language, from C to assembly, so none of that. The C processor is simply a preprocessor is simply a text substitution tool. Okay, so what it does, you will see, depending on the different preprocessor directive or command, if you will, the C processor does something that you ask it to do. Okay, so that's all it is. What is the job of it? The job of it is to prepare the text in the source file, in your C file, to the point that you desire before it is fed to the compiler. Okay, so another important thing to remember is that the C preprocessor gets its job done, creates a temporary a brand new text file that has been manipulated by the C preprocessor based on your preprocessor directives, and then it is fed to the compiler for translation. So again, there are quite a few preprocessor directives. I only will focus on two of them here with you. One of them that is very useful is called the pound define directive. Incidentally, let's remember from now on that anytime you're using a preprocessor directive, it must start with the hash or the pound symbol. Okay, so pound define is a preprocessor directive. What is the job of the pound define? It's a substitution command. Okay, so let's take a look at this example. Pound define space pi space 3.14159. So what we're saying in here, we're saying that from this point on, from this line on, for the rest of the file, wherever the preprocessor sees the symbol pi, it should replace it with 3.14159. Okay, so or we could say, you know, pound define tax rate space, I don't know, 0.31. You know, means that the tax rate is 31%. So just a matter of style. Even though the symbol here could be any alphabetic symbol, it is traditional that we use all uppercase letters for it. So notice pi is capital P, capital I. Why? Because then it catches your eye in the rest of the file. You know that it is a pound define symbol. A very useful behavior that we benefit from the pound define preprocessor directive is that numbers that are sprinkled all over your file will be, you know, defined in one single place in the beginning of your file. It's easier to look at them. It's easier to keep track of them, and makes your file more readable. Okay, so notice inside your program, if you wrote something times pi, it's a lot easier to read by a third-party reader than, you know, multiplying it by 3.14. Right, the word pi will be more, or tax rate will be more indicative of what the program statement is doing than just a regular number. Okay. That's another example, right? So we say maximum size, you know, in some context, it doesn't matter, will be replaced by 256 from now on in the rest of the code. Another very useful preprocessor directive is the pound include. Okay, so what you need to understand is when you see a line like this, or you type a line like this in the beginning of your file, it means that the contents of this text file will now be cut and paste into this location in your file just before it is fed into the C compiler. Okay, so pound include, as the name suggests, it says include the contents of this file. Okay, so it's text. It's not binary or anything, but just regular text. So what you should suspect is the file stdio.h, standard IO, standard input output.h, is a text file that contains some text, and that text will be copied and pasted into the that location in your file just before the file is fed to the compiler. Okay, so it's a very straightforward way of including text from other files into your file. Okay, the only thing you have to be aware of is there's two different forms of this pound include. Either you see the name of the file is enclosed in the wedges, you know, the greater than less than signs, or it's surrounded by the double quotes. If it is enclosed in the wedges, the preprocessor looks for it in a very specific location in the file structure on your computer. Okay, it will actually look for it for a include directory that is part of the installation of that compiler directory structure on your computer. So basic idea here is that it's looking for very specific files. Those files are called header files. Each header file contains the introductory information for each of the libraries, right? So if I intend to use the standard IO library functions, I must include the standard IO.h file in the beginning of my file, okay? Without including the header file, you will not giving all of the appropriate information about the library to your compiler, and your compiler may generate incorrect code, okay? So the second form is if you've created your own homebrew text file, just another piece of the program or some variable declarations or whatever the case might be, and you put it in the same directory, okay? So if you just put double quotes before and after the file name, it means that the preprocessor should look for it in the same directory. So very important distinction between quotes and wedges, okay? Of course, you could make this more elaborate, the second form, to be actually relative to where you are. So, you could simply say pound include some file name, whatever that file name is. All right, so in this case, I'm saying that look for it in, one level up into the subdirectory my files, okay? Just so that you're aware of it. If you're doing it in a Linux environment, of course, remember the backslashes become forward slashes. All right, so there are other preprocessor directives, which for now I will forgo. All right, so let's start looking at what the compiler actually sees. So the first elements that we would need in writing C programs. A variable, okay, is a placeholder for an entity that holds a value, okay? So in any programming language, you have different types of variables. C has a subset of those, so it doesn't have many types of variables, right? But those types include integers, floats, doubles, characters, and so on, right? So if I need to have a place in the memory that could hold a value, let's say the tax rate or the distance to an object or age of a person, right? I will define a variable of that particular type in my program. Once I declare a variable, the compiler and eventually the linker will allocate a location in the memory to hold that variable. And from that point on, when you're saying x equals 20, the value 20 will be placed in that location in the memory that corresponds to variable x, okay? So in C, it's very important that the variable must be declared before it is ever used. Other programming languages don't have this requirement. Python doesn't have this requirement, for example. So in C, if you are using a variable I, you make sure that you declare it first. Declaring it is simply the type of the variable followed by the name that you're giving it, okay? Optionally, you could do an initialization of that variable also, but that is not necessary, right? So a simple example would be int, oops, why is it switching? Int, oops, int I, okay? So int means the variable will be of type integer, space, the variable's name is I because I gave it the name I, and get used to it. At the end of every single statement in C language, you must put a semicolon. All right. So int I semicolon means that I'm declaring a variable called I, which is of type int, and I can use it later on. If you look at the next line, in this case, a variable of type integer is declared. Its name is hi. And we, at the same time that we declared it, we initialized it to 250, which means that from now on, in my program, if I don't assign a new value to variable hi, its value will be 250 until it is changed. All right, so it's initialized. Okay. It is also useful to see what you see in here. The rest of this line is a comment. In C language, anything that is enclosed between /* and */ is considered a comment. It's ignored by the compiler. It's just basically documentation. C now has also inherited the C++ style of comments, single line comments, which is /. So if I put / and put some text after it, the rest of the line, including the // are ignored. Next line, you see int low equals -40. So a variable low of type integer is declared, and it's initialized to -40. And the third one is an array. It's a result of length 20. Let's not worry about arrays just yet. So what are the most common variable types you're going to use? Int, an integer. Float, I will also suggest that wherever possible, you would use double. In fact, double is better than float. That both are floating point numbers. They're something with a fractional part. Just be aware that some of the standard library functions use only float, so then you're stuck with float. But if you have a choice, try to use double instead of float. Okay. And character is a single character, right? So if I declare a variable, char, let's say, let me write it here, char ch, that means that I'm declaring the variable ch of type character, and I could initialize it to letter J. So notice very important, single quotes. So values assigned to character type variables are in single quotes. If you put a numerical value, it will be basically the numerical value of that symbol in ASCII code. But again, I will not elaborate on that right now. All right, so you could have also qualifiers for the variables, short and long and unsigned and signed for the integer values. Let's not worry about that right now either. I'll let you guys read the slide and investigate it on your own. Variable names. In C language, variable names must follow a minimal set of rules. They must start with a letter. Okay. They cannot contain spaces, commas, punctuation marks. Okay. After the first letter, they can contain underscores or letters of alphabet or numbers. So those are all fine as long as they start with a letter. Okay. So do we have any examples? All right. So let's just quickly take a look at a few examples. This is a X is a good variable name. Why does it keep switching? My underscore, not dash. Dash is not allowed. My var is a acceptable variable name. 2x is not, because it starts with a digit, not a letter. Okay, and you get the picture. And my age with a space in between is not good because it contains a space. Either you could just leave, take the space out, or put underscore in there. Okay, so that's variable names. Global variables, if variables are declared in the beginning of your file outside of any curly brackets, as you will see later on, they are global variables, which means that they're accessible by all functions within your program. Again, scope of variables can get a little bit more complicated. Let's not worry about it right now. If you have your C code spread across multiple files, then you can declare the variable as a global variable in one file and then reference to it as an external variable in the other file. Just be aware of it. Again, we won't have any use for it right now. So let's take a look at the first C program that most people see. Why? Because at least it allows us to run a program and see how things go. All right. So the program is actually in the yellow color font. Very simple program. So we intend to use a standard input-output function called printf. So as a result of that, I need to include the header file for the standard I/O library. So put it always, if you will, if you want, always in the beginning of your file. It doesn't cause any harm. It doesn't increase the size of your final executable. Remember, this is just the text that is included that is handed to the compiler. So if you include all of the standard header files as an extreme, doesn't matter, okay? It's not harmful at all. Next, you see the word main, okay? As you will see, every C program must contain a main function. All lowercase, no capital M, no capital anything else. If it doesn't see it, it will complain, okay? So a main is a function. As you will see later on, it can receive arguments, okay? The empty parentheses in front of it simply means that right now in this program, I choose not to receive any arguments. Any function in C starts, oops, sorry guys, starts with the open braces and it ends with the closed braces, okay? So you notice main starts with open brace and ends with closing brace. Again, as a matter of style, each of these will be on a separate line. Again, to save space on this slide, I put them on the same line. The only statement within this C program is a printf function. Printf receives, in its simplest form, a string of characters within double quotes inside it. And it will print it on the output of the program, right? So we have put just basically this is a C program or hello world, which is most common first program anybody writes. So far there's nothing really strange about the printf function, except you don't recognize what this \n means, right? \n is one of the symbols that is used within the printf function. It means that basically it means what should be printed after the word program will be a carriage return line feed going to the next line, basically, right? So a new line symbol is \n. Okay, so let's pause for a moment. And since we do have a very simple program, let's actually go ahead and try to create and run this program. So I've already opened up Code Blocks, which is a open source free IDE, integrated development environment for C language and other languages as well. As a first exercise, let's actually try to create this program that we just saw. Now, Some IDEs are project oriented, which means that the executable needs to be as a result of compilation of a project. A project could contain 1 C file, 2 C files, 500 C files, doesn't matter. But you don't compile and run the C files, you compile and run the project. Okay, so CodeBlocks is a project-oriented IDE. So first thing I got to do, I go make sure we are recording. Yeah, file, new, project, file, new, project. Okay. For the context of what I'm discussing here, we only will use console application, nothing else. So the other ones you could try on your own at some other time. But console application are applications that would read and write into a terminal window. So console application go. Notice we have a choice of 2 languages. We pick C. You could give it whatever name that you want. I'm going to call it test1. You would set up what the location should be for it. Okay. I definitely don't want it to be in here. So I'm going to put it under documents. All right. And that's it. So next. And for now, just leave it as is. Finish. So what happened? A project called test1 got created, a directory underneath it called sources, and in fact, a file called main.c got created also. So let's double click on it and open it. In fact, lucky for us, it saved us some typing, because when you create a console application, by default, this is the contents of the C file. Now, you could either start adding and changing the file here, or you could simply cut and paste with someplace else and put it in here. Right now, we're perfectly fine with this program the way it is. Let's just recognize a couple of minor differences between this and what you saw on the slide. You notice here, main has the word int before it, right? This means that the function main will return an integer value to the operating system when the program exits. Okay, so int means that. Now, if you don't, it's sort of complicated, but in the Kernighan and Ritchie style C, not putting anything before main also means that it's returning an integer. It's implicit. If you really didn't want to return anything, you have to put the word void, V-O-I-D. Okay? Both of these don't return anything, but notice because I said it returns an integer, I put a sort of obligatory return statement, even though it just always returns 0, which is not a very useful thing to do, right? Normally, we want to return a value that is meaningful. 0 meaning no error, 1 means that error, whatever number 1 occurred, 2 means error number 2 occurred, things of the sort. But anyway, so this is good enough for us, all right? So next thing I do, build, rebuild. And if you had no syntax errors, you should see 0 error, 0 warnings. You always want to make sure you have 0 warnings as well. Of course, without 0 errors, you won't even be able to have an executable, but some programmers are in the bad habit of ignoring warnings. A warning is something that the compiler says, this could potentially cause a problem in the execution of your program. So make sure you have 0 warnings. Let's just, for the moment, create a situation where I would have an error, right? Remember, I said every C statement should end with a semicolon, so I forgot to put the semicolon in here. So if I say build, rebuild, notice error on line 7 says a semicolon before the word return is expected. So I put that, save, build, rebuild, and I'm good to go. Now, I can execute the generated executable by simply going debug run, or build, run rather, run, build, run. And of course, my antivirus software kicked in. It just wanted permission from me to run this executable. So that's it. So notice, what did the program do? It simply printed hello world. That's it. Okay. You could, of course, change that very easily. I could say, I am changing the text to be printed, just so that you can see. Again, you have to recompile, retranslate, and then run, or you could do build and run. If there's no errors, it will do the two back to back. And you notice program did something different. Okay, so at least you are capable of creating a new C project and run a simple program, with a one print statement or more print statements, right? So I could print multiple lines, it doesn't matter. Line 2, and you get the picture here. Line 3. So save, build, and run, which is F9 also. There you go. Okay, so let's go back to our PowerPoint slides. And all right, you can read the text. At this point, I've explained this. Okay, so let's talk about expressions and operators. Whenever you are manipulating the value of something, of a variable, you'll be using expressions. Expressions are basically the piece of code that you write to manipulate the variables, and you manipulate them using operators. Okay, so the most common mathematical operators are the add, subtract, divide, and multiply. There are other ones as well. Of course, you have logical operators, and or, and exclusive or, and so on and so forth. Okay, so what you see, again, as far as the proper wording in the C language is concerned, what you see on this side of the equation, the what I have circled, is called an expression. Okay, so and you know what this expression exactly is doing. It's multiplying m by x, and then it adds the product to variable c. So m, x, and c are variables. But now you notice something interesting. You see the value of that expression is assigned to variable y. Y equals, blah, blah, right? This is called a statement, okay? This is a statement, whereas this is an expression, right? So the value of that expression is assigned to y, and this assignment statement is now a C statement, which means that it's going to need a semicolon after it. Okay. So these are the typical operators that you're familiar with. Okay, so let's take a look at a few examples in here, right? Velocity, which is a variable, is assigned the value of the expression distance divided by time, again, two other variables. Mass times acceleration, count equals count plus 1, essentially the increment counts. This, by the way, has another form in C language. If you say count plus plus, it's exactly equal to, logically, to count equals count plus 1. Count plus plus, increment count. All right, we can do comparison, right? In an expression. 2 equals, double equal, means is it equal to, which is the most common mistake made by C programmer, right? So if you're checking if something is equal to something else, you need to put 2 equal signs between them. If you put only 1 equal sign, it's an assignment. C will not complain, but your program will not behave properly because it's not checking if X and Y are equal. It just says, okay, Y is assigned, X is assigned the value Y, okay? Greater than, less than, greater than or equal to, less than or equal to, not equal to is exclamation mark equal. So these are examples of expressions. These are not statements, right? So by themselves, they don't do anything. They only make sense if their value is assigned to another variable or if they're used inside an if statement, okay? So what you see here, it says basically, is X equal to Y or not, okay? In C language, 1 always means true, 0 means false, okay? So this expression evaluates to 1 or non-zero rather, okay? If X is not equal to Y, this expression evaluates to 0. Just keep that in back of your mind, even though this piece of information may not be necessarily immediately useful for you. Is I greater than 10? Is A plus B, should be already within parentheses, not equal C, okay? These are expressions, okay? Where do we really get used? If I say, for example, if X is equal Y, then blah, blah, which we're gonna look at later on. But just keep it in mind. I wanna make it clear, these are not statements, you know? All right, and these are logical operations. You know, if I'm hungry and I have money, I'm going to go to the restaurant. So that's that type of an and, not bitwise and operations, which are different. Okay. If X is less than 20 and X is greater than or equal to 10, which basically means what? X is between 10 and 20. So this is how we write this expression in C language. Okay, and the negation, not, right? So look at this statement. If, so whatever is inside the parentheses is the expression that the if is examining, right? Okay, it says if, oh no, I'm sorry, this parentheses, right? If not acceptable, printf not acceptable. That means that if the variable acceptable is has a value 0, not 0 will be 1, which means true, then you print it. Okay, not the best example I should have put in here. Let's move on. Okay, now, so far notice I could write a C program which basically prints this, prints that, assigns, you know, value to variable and so on and so forth, but it's very predictable in nature. You know, we don't write programs to do the same routine thing that never changes, right? What gives power to C language is capability to do different things that are not known necessarily at compile time. At runtime, it may encounter different situations. So a couple of control statements that are of interest to us are looping, repeating, and conditional statements, if type statements. So let's look at the if statements, okay? The if-else statement in C language is as follows, right? If followed by an expression that it is being tested. If that expression resolves to, has a value of true, which is non-zero, then whatever statement comes after the if will be executed. Otherwise, the other statement after the else will be executed, right? So let's pretend for a moment that result is equals 60 for a moment, right? So let's take a look at here. Let's take a look at the expression first. Is result greater than or equal to 45? Is 60 greater than or equal to 45? The answer is yes, true. And remember, true is non-zero. Let's say it's 1, right? So, and the if statement looks at the result of the expression, 0 or non-zero, right? Because the expression was non-zero, it was true, so this statement will be executed. If result was, I don't know, 23, 23 is not greater than or equal to 45, the expression would have evaluated to 0, else would have been executed. Okay, so since we're at it, let's very quickly run a program like that together. I'm going to just basically be lazy and use the same file in here, right? So I'm going to say int I and j. So I'm declaring two variables, I and j. I'm going to say I equals 7, j equals 9. Now look, if I is equal j. Now, a good matter of practice in C language, only the first statement after the if statement is associated with the if statement. A lot of times you want to do more than one thing if the condition is met or is true. So make it a habit, always put whatever that you want to be associated with the if inside the curly brackets. Notice in this editor, as soon as I put the start curly bracket, it puts the end curly bracket also, right? So I'm going to say printf, they are equal. And of course, I want to go to the beginning of the new line, okay? Now, you don't need to have else, okay? It's only your choice, okay? So in fact, let's not put an else in here and run the program. So first of all, should we see this printout or not? Well, 7 and 9 are not equal, so I should not see this line printed. Okay, so let's go, let's save, and then build and run. Notice you didn't see that statement printed. Now, let's add an else. Else, copy and paste. All right, they are not equal. So notice now, if I run the program, the second statement should be printed. Okay, let's just press F9. And you notice they are not equal. All right. Now, let's just make them equal. I think everybody knows what's going to happen in here. And they are equal. Okay. Now, you look at this program and you say, okay, I like the if statement. I know what to do with it. But philosophically, this is a very dumb program. When I'm writing the program, I know I and j are equal. Why do I need to write a program to tell me they are equal or not? And your argument is absolutely valid. Okay. We don't write programs that have outcomes that we already know. Okay. We write programs that the outcomes could, is unpredictable. So in this case, I and j, being pre-assigned values of 9 is kind of silly. Okay. A more realistic situation would be that I would enter the two values through the keyboard. Okay. Now, there are many, many ways of inputting values through the keyboard in C language. Let's take a look at one or two ways that could be useful for you. One of them is to do this. I mean, you could just simply copy the code and use it always like this, but let's understand what this means. First of all, I declare a variable called buff, which is an array of 10 characters, right? So just think of it this way. I've declared a array in the memory that can hold up to 10 characters. Now, now that I have that location in the memory assigned to my program, this is a standard I/O function. Get S means get string, means get a, read a string from the keyboard. Okay, so it says, okay, if it gets a string from the keyboard, where does it put that string? It puts it in location buff. Okay, so a variable buff will now contain the string that was received through the keyboard. I don't want, in this particular case, I don't want that string to be treated as a string. I want it to be treated as an integer. Okay, so there is another C function, library function called A to I. A meaning character, I meaning integer. Character to integer conversion. Okay, so notice I'm basically using two built-in functions. One of them reads a string from the keyboard, the other one converts it to an integer, and now that I have it, I will assign that to variable I. Okay, of course, be user-friendly. How does the user know that they have to enter I? So printf please enter I \n. Okay, now I'm going to repeat the same code for J. So please enter J, and in this case, J will be assigned what's from the keyboard. So now notice I read I and J from the keyboard. Okay, now my program makes a determination whether they're equal or not. Makes it a little bit more interesting. So let's save and build and run. All right, so notice it says, please enter I, 23. Please enter J, 23. They are equal. Okay, let's run again. Now this time I could just simply show you another way of running, which is pressing on that play button. Please enter I, 678. J, 44. They're not equal. Okay, so you get a picture. All right, so very powerful feature. If statement makes decisions for you. Okay, and you also learn how to enter, one way of entering integers from the keyboard, right? Let's just make one more change to this to beat this to death. So I'm going to say if I is greater than or equal to, right? Remember, greater than or equal to. Okay, so if I is greater or equal to 18, or let's say 13, I can go to PG-13 movies alone. All right. I'm not making a decision on J, so let's comment this out. Remember, I said you could do double slashes, and that means that that piece of code right now is commented out. The compiler will ignore it. Okay, and right. So in this case, I'm basically comparing I to 13. If it is older than 13, you can go to PG-13 movies. Otherwise, you cannot. So save, build and run. All right. So please enter I, 24. 24-year-old should be able to go to PG-13 movies, right? So I can go to I being the name of the person, obviously, to PG-13 movies alone, right? Let's run it again. Person is 6 years old, so cannot go. All right, so let's go back to our slides. And that's basically examples of if and if else. Let's do one more thing, and then well, I'll end this video and we'll continue on the next video. So another way, another rather situation where you may be interested in using if statements is if you want to do multiple comparisons. Okay, so the idea is this. Okay, I'm going to do the following. Okay. I'm going to create a menu. Okay. Please enter. Okay, so printf menu 1. I don't know. Lights on. 2. Lights off. 3. Fan on. 4. Fan off. And let's say 5. Quit. Okay. Let's make sure I put this within double quotes, or I'm going to get into trouble. Let's put a \n in here, right? So just basically creating a scenario where there's a menu that the user can select 1, 2, 3, or 4, or 5, right? So I just print what the options are. Now, and I said, please enter your choice. Okay. This is fine. I don't need a J anymore. Okay. So now take a look. If I equals 1, printf, of course, I have to do something rather than just echoing it. Okay. I would say lights are turning on. Okay. Now pay attention to what I'm doing now. I'm saying else. Else means if I was not 1, but it could be 2, 3, could be anything else, right? I say, okay, what if it was 2? Right? Equals 3. Okay. Fans are turning on. Okay. Fans are turning off. Of course, remember, I put actually code in here to turn the fans off or on. Right now I'm not. I'm just putting a print statement in here. And I would say else if I equals 5, exiting menu, which takes you to the upper menu or whatever. It doesn't matter right now. We're just making a fake scenario here. Okay, so notice this is a situation where I have multiple levels of a statement, right? If it's equal 1, do something else. If it is 2, do something else. Else, if it is 3, do something else. So on and so forth. This is perfectly legitimate. Let's just run it, actually, right? Build and run. All right, so enter your choice. I'm going to enter 3, and it says fans are turning on. By the way, you notice that this is kind of silly because it just reads the, the choice from the menu once and it ends. So I'm going to basically jump in front of myself and create an infinite loop in here. Infinite loop while 1 means while forever, and I put everything that I just typed inside the while loop. Now, one thing I want you to notice is that indentation, even though indentation white space is ignored by C, it is very useful for the human reader, right? So notice the while starts here and ends here. Most editors actually highlight the beginning and end matching ones to make sure you're not mismatching your braces, right? The curly brackets. And then whatever that's inside of it is indented. So that means what? I print a menu, I get a choice, I print the result, go back, wait for the next choice in the menu. So this runs forever, right? So if it runs forever, then 5 should actually, get me out of the program. So I'm going to say exit 0, which is something new you haven't learned. Exit actually exits the program. Okay, so keep that in mind. Now let's build and run. All right, so enter your choice. 1, it prints it, and as soon as it prints the result, it will go back and wait for the next menu choice, right? See, lights are turning on. 2, lights are turning off. 3, fans. 4, fans. 5, exiting menu, program ended. Notice I'm done. Okay, so this is all fine. Let me show you another way of doing this. Okay, and that's using the switch statement. Switch statement is useful when you're comparing to specific, not ranges, specific values, 1, 2, 3, A, B, C, D, things of the sort, right? So what I'm going to do now, I'm going to comment out this entire piece of code. All right. Notice I put it between */* and */. Green means it's comments, right? But now I'm going to rewrite the code in a different way. So I'm showing you 2 different ways of doing the same thing. So while 1, print, right? So instead of if statement now, I'm going to say switch. So notice how the switch statement works. Means switch on or make a decision based on the various values of I. Okay, now case 1 : break. All right, so I want you to compare, and of course within switch statement everything is going to be indented, and I need another brace to end the switch statement. So look, within the switch statement, right? Rather than saying if and then in curly brackets put what you do, you say case, cases, and notice all the keywords, by the way, in this editor are highlighted in dark blue, right? So this is a reserved word in C. Case 1 means what? If I is 1, do whatever that you want to do in here. You could put 15 statements in here if you wanted, right? But then you end it with break. Break means get out of the switch statement, right? Because once you find the match, you want to get out, okay? So if 2 becomes case 2, okay, lights are turning off, okay, and then of course break, and you get this, you get the picture. All right, so I'm going to skip the other ones, all right, and I'm going to say case 5. All right, and now what's very important, good programming, you don't have to, but always put a default statement. Default means a catch-all if it's not 1 or 2 or 5, right? or one, or, so whatever that you've listed. Default simply means, what the choice of the value of I was not in the list above. Okay, so in this case, I could say invalid choice. All right, so notice now, rather than putting if I equals 1, do something, else if I equals 2, do something, I say switch I, case 1, do something, case 2, do something, case 3, do something. Let's not forget our break here, right? And then at the end, you always put default and a catch-all for, anything that is not in the list above. So let's save this, build and run. It should behave exactly the same way, right? So if I enter 1, it prints lights are turning on. 2, lights are turning off. Of course, I was lazy. I could have added 3, 4, or 5. In this case, 5 should exit the program. Done. Okay, so now you also learned that switch statement is another way of writing multiple nested if statements, as long as the values that we're checking are singular values, okay? Integer values or character values. Switch statement doesn't work with ranges, so you can't say switch, I greater than to whatever or less than, it has to be equal 1, equal 2, equal 3, and so on and so forth. So let's stop at this point. This is the end of this video, and the next video will pick up from the next slide on.